Okay, we work on this indeterminate beam. We try to analyze it by using the integration method. And when we do the discretization, we find out that there are 3 degrees of freedoms, 3 unknown displacement boundary conditions actually for each member, right? And then we draw the free body diagram. And from the free body diagram, we said that the moment at these ends of the member are equal to 0. And while writing the moment equation, we use that information, and this way we write our moment equation in terms of the end moment BA only. And again, likewise, for the second member, we use the information that moment is equal to 0, and by using that information, we find out that, or we have written the moment equation in terms of a single end moment. And then we continue, we write down the differential equation, and at the end of the day, we needed only one boundary condition, one unknown boundary condition, and we were able to relate the end moment BA with theta B only. And again here, we were able to relate moment BC with theta B only. And then we write down the equilibrium equation. We have one unknown and we only need one equilibrium equation, and we determine what theta B is. Okay. Now I will analyze the same problem by using the slope deflection equations this time. So I have, let's draw the figure one more time. This is 24 kilonewton meters. That's point A, that's point B, that's point C. This distance is 8 meters, and that distance is 6 meters. And remember that again in this problem we said that I did all these calculations, all these integrations to relate the end moments with the end displacements. And we said that what will happen if I can develop this relationship for the most general case, right? And that's the way we derive the slope deflection equations. Let me write it here. So we derive 2 different slope deflection equations. The first one is for the most general case, right? We took a member. We said that I have a moment at this end. Let's call it MAB, and another moment NBA, right? This is point A, this is point B. And we said that under this end moments, this structure will move as follows. I have YA here, that's the deformed shape, YB, court rotation. We define the court rotation in the counterclockwise direction, and I have theta A in the counterclockwise direction, theta B in the counterclockwise direction, and that's the deformed shape. And then we said that under this given moment, if we have the following deformed shape, MAB is equal to 2EI over L 2 theta A plus theta B minus 3 times the court rotation. And we may have any loading here, and we calculate the effect of loading by writing down the fixed arm moments, fixed arm moment AB. Now moment BA is equal to 2EI over L. I got theta A plus 2 theta B minus 3 times phi angle plus the fixed arm moment BA. And this is the case when we have moments at both sides, and we have 3 deformations are defined by using these 3 parameters. And we also derive a version, we call it modified slope deflection equation, for a specific case. In that case, we said that, okay, that's my member under certain loading. And here I have MAB, but at this end, I know the moment is equal to 0, or this end is free to rotate. In that case, my deformed shape will look like this. So here again I have YA, I can have YB. This relative translations are defined by court rotation, phi angle. I have theta A here, but the far end is free to rotate, so we will expect to see a deformed shape like that. So in that case, I have the phi angle and theta A as my unknown parameters, because remember that while driving that equation, I use this information, moment is equal to 0, and this helps me to relate this moment with these two deformation parameters only. I didn't need to know, I didn't use the rotation at point B. And that relationship will be equal to MAB, the modified slope deflection equation, is equal to 3EI over L theta A minus phi plus fixed end moment modified AB. So we drive these two cases. Let's again repeat one more time. In the first case, I use the displacement boundary conditions phi, theta A and theta B, and these are the two equations that I drive. In the second case, instead of using the displacement boundary condition here, I use the force boundary condition. In other words, I said that the moment is equal to 0, and I come up with a simplified equation. We call it modified slope deflection equation that depends only two displacement parameters. So let's go back to our problem. Let's do discretization. So I have node A, node B, node C, and we have three rotational degrees of freedoms, theta A, theta B, and theta C. So basically this tells me that I got 3 degrees of freedoms. Now let's draw the free body diagram. But before that, this is my first member, this is my second member. Now the free body diagram. A uniform distributed load here, a uniformly distributed load here. Let's show the end moments. I'm just showing every one of them in counterclockwise direction. So here I have MBA, that's MBC. Now I will use that the moment is equal to 0 information. Since I know the moment is equal to 0, while writing the slope deflection equations, I will use the modified ones. Okay, so basically, if you think about it, if I use the modified equation for this member, instead of using this boundary condition, I'm using the moment of equal to 0 information. Okay, and the same thing holds true for the second member. Instead of using the value of theta C, I'm using the moment of equal to 0 information. Now after doing that, I have to write down the slope deflection equations. Let's do it for member 1. So I have MBA is equal to 3EI over 8 theta B, and we minus phi plus fixed moment BA. Now, since we don't have any translation degrees of freedom at these nodes, it means that phi angle is equal to 0. And if you work on this problem for this given uniform distributed load, you will find out that the fixed end moment BA will be equal to W L square over 8. And then the final version of this equation will be equal to 3EI over 8 theta B, and this is minus 24 times 8 squared divided by 8, and that's equal to 3EI over 8 theta B minus 192. So with 2 steps we were able to determine this equation. So here, in order to find out that equation, I have to do this calculation, do the integration, and come up with the following equation. But instead of it, I just use the slope deflection equation, the one that we developed for the most general case, and obtain the same relationship. Now let's do it for the second member. Member 2. I got MBC is equal to 3EI over 6 gain theta B minus phi plus 24 6 squared divided by 8, and this gives me EI over 2 theta B plus 108. Again, if you go back to this example problem, now we obtain this equation with only 2 steps. Now we relate the end moments with the unknown displacements, right? If you think about it, if you just take a look at these 2 equations, I don't have theta A nor theta C in these equations. Why? Because I use these 2 force boundary conditions. Now, as a final step, let's write down the equilibrium equation. So in order to write the equilibrium equation, I am transferring these moments to node B. So I'm writing down the moment equilibrium equation at B, which is sum of moments at B must be equal to 0, and this tells me that MBA plus MBC must be equal to 0. So 3EI over 8 theta B minus 192 plus EI over 2 theta B plus 108 equal to 0, and this equation gives me that theta B as equal to 96 divided by EI. And if you put this value theta B into these 2 equations, we obtain MBA as equal to minus 156 kilonewton meters and MAB as equal to 156 kilonewton meters. Okay, so as you see, instead of doing all these calculations, right here, I solve it in very simple steps. Again, in this example, I will be working on the same problem. This time I won't be using the modified equation, okay? I will just use the displacement boundary conditions in my solution. So that's point A again, B and C. That's 24 kilonewton meter. So this is 8 meters. And that's 6 meters. Okay, let's do the discretization. So I have theta A here, theta B here, and theta C here. Now let's draw the free body diagram. And as you see, we have 3 degrees of freedom here. So let me draw the free body diagram now. I have a uniform distributed load here, uniform distributed load here. Now here I have MAB, I got MBA, I got MBC. They are all defined in counterclockwise direction because that's the way I derive my slope deflection equations. So these are the end moments. Now let's transfer the end moments to the nodes. So the equilibrium equations I have is at node A, the sum of moments must be equal to 0. That's my first equilibrium equation. This comes from, okay. At node B, sum of moments must be equal to 0. That gives my second equilibrium equation. So these are all nodal equilibrium, moment equilibrium equations at nodes. And MCB is equal to 0. Again, these are the, so as you see, I have the moment equilibrium equations. And that moment equilibrium equations give me these 3. And as you see, I got 3 unknowns and I have 3 equilibrium equations. Remember that while writing the slope deflection equations, I didn't use the information that MAB equal to 0. Instead, I apply this requirement while writing the equilibrium equations. Alright, so I didn't use any modified case in that case. Now let's write down the slope deflection equations. That's member 1. That's member 2. Again, since I'm not solving any differential equation, I'm not showing any local axis for these members because we don't need it anymore. We are not solving any differential equation, right? So I just exclude them. Now, let's start from member 1. So MAB is equal to 2EI over 8. 2 theta A plus theta B. There's no coord rotation because there is no translational degrees of freedom, plus the fixed end moment, which is equal to 24 times 8 squared divided by 12. This is 1, this is 2, this is 1, this is 4. So my equation of MAB is equal to EI over 2 times theta A plus EI over 4 theta B plus 128. And MBA is equal to 2EI over 8. This time I have theta A plus 2 theta B minus 24 times 8 squared divided by 12. That's 1. So MBA is equal to, I have, this is 1, this is 4, so EI over 4 theta A plus EI over 2 theta B minus 128. So these are the slope deflection equations for the first member. So let's write it for the second member. So I have MBC is equal to 2EI over 6 2 theta B plus theta C plus 24 times 6 squared over 12. That's 1, that's 3. So MBC will then be equal to 2EI over 3. No. Yes, 2EI over 3 theta B plus EI over 3 theta C plus 72. And MCB is equal to 2EI over 6 theta B plus 2 theta C minus 24 6 squared over 12. That's 1, that's 2, and then MCB will then be equal to EI over 3 theta B plus 2EI over 3 theta C minus 72. And these are the equations for the end moment. So as you see, the end moments now depends on theta A, theta B, and theta C. So here, remember that I didn't use m is equal to 0 information here. So all my moment equation depends on all these rotational degrees of freedoms. I got 3 unknowns, 3 equilibrium equations. So let's write it down. So the first equilibrium equation is sum of moments at A equal to 0. This tells me that MA equal to 0. Then EI over 2 theta A plus EI over 4 theta B is equal to minus 128. The second equilibrium equation is sum of moments at B equal to 0. This tells me that MBA plus MBC is equal to 0. then EI over 4 theta A plus EI over 2 theta B minus 128 plus 2EI over 3 theta B plus EI over 3 theta C plus 72 is equal to 0. And if you evaluate that, simplify that equation, at the end we have EI over 4 theta A plus 7EI over 6 theta B plus EI over 3 theta C equals to 56. We need one more equation, which is sum of moments at C equal to 0. So then this is this should be AB, then this should be MCB equal to 0. And our equation will then be EI over 3 theta B plus 2EI over 3 theta C is equal to 72. We needed 3 equilibrium equations for the 3 unknowns. Now we can solve it. Solution. I will write these equations in matrix form. So EI 1 over 2, 1 over 4, 0, 1 over 4, 7 over 6, 1 over 3, 0, 1 over 3, 2 over 3. Got theta A, theta B, and theta C. That's equal to minus 128, 56, and 72. Okay, and if you solve the system of equations, you will obtain theta A as equal to minus 304 divided by EI. Theta B is the same, 96 divided by EI. And theta C is the same, 60 divided by EI. Now if we put these numbers into the moment equations, we find out that MAB is equal to 0, which should be MBA is equal to minus 156, MBC is equal to 156, and MCB is equal to 0 again as expected. Now if you think about it, I solved the same problem, but this time it took much longer. I did a lot of calculations because I didn't use this force boundary condition while writing these slope deflection equations, which requires 3 unknowns, and I obtain all the unknowns, the values of all these 3 degrees of freedom, then calculate the moments. But if you go back to our previous solution, this one, now I use the modified equation, and the modified equation helps me to eliminate the calculation of this rotation. Again, I use modified equation for this member, and it helps me to eliminate the calculation of this C, and I end up with only a single degrees of freedom. Okay, so from now on, in order to simplify our solution, whenever we have a free to rotate condition or moment is equal to 0 condition, we will be using the modified equation. Otherwise, we have to do a lot of extra calculations. And as I said before, from now on, I will be using this in my discrete structure. I will say I will be using the modified equation, and no need to calculate theta A. Again, I will say I will be using the modified equation for this member, and this way I don't need to calculate theta C, and I don't have 3 degrees of freedom, but I got 1 degrees of freedom. And from now on, I will be showing the discrete version of the structure as follows. I will only show the degrees of freedom that I need to calculate its value.